Alright, hell yeah. So this is the rotating disc problem, and I'm going to go over one aspect that's pretty cool. Because part of this problem requires you to know the slope of this line. You know what I mean? If I bring down this component and make a right triangle, I want to know the rise and the run of this slope. Because of that, then I can come over here and draw a perpendicular to this. And this is going to be the direction of the angular momentum of this spinning system. So this whole spinning system is rolling this way about the z-axis, and hell yeah. And the center of mass is going to be like right there. The distance away to it is going to be there, and then we're going to have a tangential velocity related to the angular speed of this whole system about this axis. And so, but you can take the angular momentum about this point, you're just going to get a vector in this direction. So at some point in this problem, you need to get the component that's in the z direction. That's kind of what they asked for. And it would be nice if you could just do a little ratio. Some of the problems out there say, they just say, hey, let's find this angle. And that's fine, you know what I mean? Because right here you have another right triangle where this is your hypotenuse, and this is two legs of this right triangle. And so the angle here is going to be an inverse tangent. That's going to be an inverse tangent of the opposite over the adjacent. In this problem, you don't have to work with this big triangle. You can just work with the smaller one. If you worked with the big one, it would be 2a. That's opposite opposite over adjacent. Adjacent's 2l. For this problem, L is going to be the square root of 24a. But it makes more sense to work with the smaller triangle. Okay, but in this video, we're going to do a shortcut where we show that, well, check this out. So let's grab this, and if here is the right triangle, this is what I'm just going to do. I'm just going to rotate it just like this to where now this is flat. And now look at this. This is our slope. You know what I mean? So check this out. So this slope right here is going to be the same as when we go flat. It's going to be the same as this slope right there. And that was I just didn't really see it. I actually spent quite a bit of time trying to find this slope based on knowing, you know what I mean? You get this hypotenuse is 10a. That's just Pythagorean's theorem. 2a squared plus 2l squared. And you substitute that 24a. That's going to be your L. And then you get 10a here. But still, I still wanted to figure out the rise and the run. And so I did kind of something tricky. I said this 2l, that's going to be the square root of 2 times square root of 24a. And then I just kind of got rid of the a's. So this is 10, this is 2, this is 2 square root 24. But then I had to figure out this distance. I had to figure out this distance and this distance. So I said, well, let's say this is x, and this is just going to be 10 minus x. And then I use what I know about. I know that this side to these two triangles is going to be the same. This is the hypotenuse. So I said that, hey, 2 squared minus 10 minus x squared, that's going to equal this squared. So we have 24 squared minus this side squared, which is just x squared. And so that's what I did. And you know what I mean, just way too complicated, just to show that it's so fascinating. And I'm just going to do a quick little proof. You know what I mean? And this is just more of a visual proof. Let's say I have a 45-degree angle. We would all agree that this is 45. And then I have a slope of 1 and 1. And then I have this right triangle. So, you know what I mean? What I propose is that, like this, so if I have this triangle, it doesn't matter. Let's come down here. Let's say I put this triangle flat. So this is side of 1, this is 1, this is about 1.4, square root of 2, right? So let's do 1.4, and then let's go 1 and 1. So if I put this triangle kind of up onto its hypotenuse, this angle don't change. You know what I mean? So, yep. So, and I'm going to mark this. I'm going to put 2 hashes there and 2 hashes there to show you that. And then I'm going to flip it right here. So, well, I'll put 3 hashes on the hypotenuse and then 2 just to show you, like, hey, we're working with the same angle. So this is going to be the 3 hashes there. So all I did is just flip it. And that might be the most interesting part about this video is, I mean, I've done this before, but I just kind of forgot about that. And there might be a better proof out there. But if you take a 3, 4, 5 triangle, I can put the triangle, oh, bummer. I got to do this. So this is going to be 3, 4, 5. But now this is the angle that I'm interested in. So if I put the triangle this way, this is the angle that I get. And I'm still in that same boat. It's just like I don't know what this rise is, and I don't know what this run is. But I know that this rise and this run is going to give me a slope, and that slope is going to be a number. But that slope is going to be related to this angle. So that was the other thing. It was just so fascinating to me that whatever angle I choose, let's say I choose this angle, it's representative of a slope. If I choose some new angle, then that's going to be a slope. But every angle is representative of some sort of slope. So that's kind of what I kept, in my mind. And so we took this 3, 4, 5 triangle, and then, oh, what the hell? So I guess, but yeah, no, it's the same triangle. So yeah, it's so fascinating that this angle's right there is the same on that side. I guess I just have to flip it over. So again, we have this 3, 4, 5 triangle. This is the hypotenuse. I'm going to take the same angle and flip it up like that, and it fits right in. And so now I know the slope of this. The slope of this line is going to be a rise of 3 and a run of 4. So the slope is 3/4. Sweet. So now I can do that same thing just in reverse. So our problem, given the rotating discs problem, you had something where you had this perpendicular, your hypotenuse was on the x-axis, and I just needed to know this slope. And so now I just know that this slope is going to be this rise over this run. Because, visually I can see that. I can see, like, hey, if this is just my representative axis, then I'm going to go up and then over, and that's going to be my rise and run. Now, and let's talk about, so hell yeah. So yeah, so I drew 2 pictures, because if we do this is our problem, and then I do that same, hey, I don't know the slope of this, because I don't know this dimension and I don't know that dimension, so I'm just going to flip it like this, and then this is flat now, and then sweet, so the slope of this line is down, and then, well, it's going to be like down and then over. So I do get a negative slope, but that's why I just chose to print this backwards. So all I did is just kind of flipped it over. So this is kind of the mirror image. And so now we're just good to go, because now I can get this horizontal, and now I'm interested in this slope right here. So this slope is going to have a rise of 2 and a run of 2L, which would be 2 square root 24. So, and let's do this. And that's just for this bigger triangle. Might as well use the smaller triangle. The smaller triangle is going to have a rise of 1 and a run of 24. So let's do that. Slope is 1 divided by the square root of 24. We're going to rationalize. And so, so we just multiply top and bottom by 24. So we get the square root of 24 on top, and this just becomes 24. So hell yeah. So that's going to be the slope. Let's go back to our problem. So now this slope right here is going to be a rise of 24 and a run, damn it. So this slope was a rise of square root of 24, run of 24. Sorry I said that wrong. But so we have a rise of square root of 24 and a run of 24. All right, hell yeah. So then, and for this problem, you do need to know how to take the slope to a perpendicular. But that's fairly straightforward too. Especially if you have, like if here's my axis and I just kind of take a sliver this direction, perpendicular is going to be that direction. So let's say I go like 10 this way and up 1, then I can totally see that I go 10 this way and up over 1 there. So this slope is going to be rise 1/10, And then this is going to be, anytime that you have a perpendicular, it's going to be inverted. So it's going to be 10 over 1, and then we have a negative. So we have this slope is going to be negative 10, and you can see that we have a slope downward of the rise is negative 10, the run is 1. So we go down negative 10 over 1. That's going to be the slope of that. All right, so hell yeah. So yeah, this problem just required that you it's very easy to find the angular momentum about like any particular axis that's perpendicular to the stuff that's going on. But then if you need to find the component up against here, then you need to use that ratio. So and then let's finish the video with that. And yeah, we got hella time. So so let's do that. So that was the 2 steps that I wanted to do for this video. Is like, okay, so we have this is our slope, and we figured that out. And then we have to get it up here. So if this was a rise, so again, this is a rise of square root 24 over 24, then the slope right here, just by that rule, is going to be negative 24 divided by the square root of 24. And isn't that what we have? So this is going to be the square root of 24, 24, and so we have a rise over run. We have, and it's going to be a negative slope, so we have negative 24 and a run of square root 24. I'm going to rationalize this, and so this gives us 24 square root 24 divided by 24, and so our slope is going to be negative square root 24 divided by 1. Sometimes it's useful to do that, you know what I mean? So now we have a, we're going to go up 1, and then, so our slope is a negative. It's going to be a negative, and then even this, what the hell is negative square root 24? That's about the square root of 25, so you can kind of just see that this is a slope of negative 5. So sweet, and the slope right here is going to be a slope of positive 1/5. That's going to be 0.2. So just enjoy. It's always nice to do that. But hell yeah. So we're going to take, now what are we going to do? Oh yeah. So to actually find the percentage, so we're going to get, let's say the angular momentum, for the problem is going to be like 100. 100, that's going to be the angular momentum. Whatever units angular momentum has, but hell yeah. So we have a vector of 100 in that direction. We want to know how much of that is in this z direction. Well, we take this this triangle right here. We take this triangle that has 20 dimensions of 24, square root 24, and we still need to know the hypotenuse. Because at the end of the day, if we knew the hypotenuse, then this number, 24, divided by the hypotenuse, that's basically the percentage. This is the fraction of the whole. So anytime that you have a hypotenuse, these components of the triangle in, let's say, the y direction and the x direction are the percentage of that hypotenuse in those directions. And so also it's just good. So let's actually do this. So if we're going over 1 and then 5, so that's 3, 4, 5. So this is kind of our slope. We have kind of negative 5. Well, let's say if this is 5, like, hey, this can't be more than, this is about like 5.1, let's say. So and if so right here, so if this is 1, 2, 3, 4, 5, kind of graphically representing this is kind of interesting, because maybe I have just about, this is approximately 5, because I mean these 2 lines are about the same. Now this is 1. So this component is basically 1 over 5, and this is 0.2, which is 20%. So this component right here in that direction is 20% of the hypotenuse. But you can see that if this is 5 and this is 5.1, this is virtually 100%. And but you know what I mean, it's going to be like 97%. So the percentage here is going to be like 0.97. So it's always good to know what these problems would be from like a fractional perspective. Because yeah, like at the end of the day, probably for this problem, you might be able to just solve for this vector, and like it's just going to be slightly less. Whatever this is, like this is going to be like 97. You know what I mean? It's going to be 0.97, whatever that vector was. Okay, but let's do it as a fraction. So so we have this triangle. has side 24, square root 24. I want to know the hypotenuse. So it's just Pythagorean's theorem. So we're going to take this side squared, that's going to be 24, plus this side squared. That's going to be 24 squared. And then we're going to take the square root of that. That's going to be our hypotenuse. All right, so 24 squared is 24 times 24. Let's just bust this out. We got 8 and 4, so we have 576. So I have the 6, I have a 17, and then I have 576. We're going to add that. So that was that part. We're going to add that to 24, and we're going to get 0, a 1, a 0, and a 6. So hey, we have 600. Now it's a good skill. So we have to take the square root of 600 because that was in there. And let's factor out 100. So we have 100 times 6, and that's the same thing as doing that. You know what I mean? And so that's going to be 10 square root 6. So hell yeah. So now we have this triangle. We have 10 square root 6. And now I know the fraction of this component. So this component is going to be, so this, the percentage, quote unquote, or the fraction of the whole. All right, hell yeah, we're back. And I already went over this, but let's do it on a new sheet of paper. So we have this triangle. We have the hypotenuse is 10 square root 6, and we have the two sides. And so we want to know, if we have a vector right here of 100, we want to know the component in that direction. So we're going to take this side of the triangle, 24, and divide it by the hypotenuse, 10 square root 6. And when we do that, this right here is a percentage. It's going to be like 0.98. Yeah, it's more than 0.97. I already did this. So anyway, and yeah, let's carry this through. So we can say this is 12/5 square root 6 on the bottom. Then I can rationalize, and so this becomes 12 square root 6. Bottom becomes 5 times 6 is 30. And so I can factor out a 2. So we got 6 square root 6 divided by 15. All right, so sweet. So that's kind of reduced into its lowest form. And so let's type this in. So we got 6 square root 6 divided by 15. And so hell yeah. So that is going to be 0.9798. And hell yeah, you get 0.98. So that's pretty sweet. And it just shows you as a fraction, because there was some other math people, YouTubers, math YouTubers that did this problem, but they kind of did what most everyone would do, is just like, well, I'm pretty used to figuring out sines and cosines. So I know that, hey, I can get this angle from an inverse tangent. Once I know this angle, that's the same thing here. And if I know this angle and then this vector, then it's just going to be the cosine component. So I'm just going to take this 100 cosine of that angle. But, the whole idea with these JEE problems are like, hey, you don't get a calculator. So a lot of this you'll have to use fractions, rationalize. But, even for this one, this is probably overkill. You might be able to solve this even without doing that, just because, 100% and 0.98%, that's one of those just intuition, you know what I mean? Well, hell yeah, like this component, you know what I mean? This component's going to be 20%. So if I have a vector of 100, hell yeah, in this direction, if that's what they're asking, that's going to be about 20%. But in the vertical direction, it's damn near just the actual vector. And even for angles like 30 degrees, hey, this cosine component is going to be 0.866. That's 86.6%. Even there, if I'm just doing a rough average on problems, I'm going to call this 100%. And I know it's 50% right here. And, and I know that 50% plus 100%, that doesn't really matter. But it's more of squaring this. 0.5 squared plus 1 squared. Well, I know that's going to be greater than 1. But still you're pretty safe to overestimate this cosine. Any angle that's going to be less than 30 degrees, you can almost just guess that this cosine is going to be 100%. If this is your hypotenuse, this cosine component is also your hypotenuse. You know what I mean? And but hell yeah, it doesn't take a small angle for this to have like, 20%. We got a tiny angle. This angle is like 11.56 degrees. And we still have a 20% component of the vertical, in that, of this hypotenuse in that vertical direction is going to be 20%. All right, so sweet. So I think we're going to be done with this video. I think this is the secret sauce. Hopefully maybe do a shorter video, but hell yeah, 3, 4, 5 triangle, that's that angle, and we can put this hypotenuse right on this axis, and that's that same angle. So hell yeah. So if I was given this, which we're totally in our problem, so let's show you one last time. We are given a triangle that looks like this. This is the hypotenuse, and then we have a 90-degree, right triangle here, and it's just like, well, I want to know the slope of this. What's the fastest way? Well, I already know. It's just like, hey, now I can just visualize it. I'm just going to make this my axis, and then say, hey, this is the rise, and then this is is that right? So hell yeah. So if I'm starting here, yeah, it's bizarre, but hell yeah. So you just flip it like this. This is my axis, and then, oh, okay, now I can see. I get the slope of that. Well, and this is what I'm saying. Sure, the slope of this line is related to this angle. So that therefore, hey, isn't this angle related to the slope of this line? Yes, the slope of this is going to be the same thing as the slope of that. You know what I mean? The only difference is a negative sign. So I guess I pointed that out where you have to invert this. So hell yeah. So I think I'm done. This was pretty satisfying. None of my videos are crispy and polished, but this one was at least under 3 hours. Alright, thanks for joining me, and that's the video.